So now we'll get started. So good afternoon. My name is David John Gagne. I'm a machine learning scientist at the National Center for Atmospheric Research in Boulder, Colorado. I'm calling in from Longmont, Colorado, working from home like everyone else is these days. And kind of the idea behind this whole mini tutorial is this machine learning, cloud physics in the cloud. So I wanted to kind of go through sort of the practical steps of like training different kinds of machine learning models, doing some interpretation, loading data from cloud data sources, and kind of doing some analysis relevant to cloud physical properties. And we're going to do this for two data sets. The first is called the Microphysics Data Set. You can, in the notebook itself, you can read a bit on all the kind of greater details about it here. The main takeaway for this particular problem is that what we're trying to do is accelerate the bin microphysical parameterization schemes. For those who are not as familiar with microphysics, first, microphysics is the idea behind microphysics is that we want to have a model for the interactions of different water drops and droplets and ice crystals within clouds. Occur on kind of microscopic level to slightly small macroscopic level, but the heat transfers and other interactions involved propagate upward all to the global scale. So it's a very multi-scale process, spans a lot of orders of magnitude, a lot of energy is involved, drives the formation of clouds, how thick the clouds are, and then how thick the clouds are affects the Earth's radiative balance, and it's one of the biggest uncertainties in our climate models. Basically, if even small changes in how fast you go from kind of cloud droplets to raindrops, and how fast the raindrops fall out of the cloud basically affects how much sunlight is reflected by the clouds, and thus whether it can attenuate the global warming signal or amplify it. Our current climate models use a relatively simplified microphysics parameterization. So pretty much every weather model, they're still very powerful and represent the processes pretty accurately, but there's some limitations associated with them. In particular for cloud microphysics, we assume that the distribution of cloud particles of different sizes is kind of a gamma distribution roughly. But there are cases where gamma is not always the most appropriate distribution, and there's also all kinds of little interactions that go on between particles of different sizes that we just assume occur on a bulk scale that may not necessarily be true in all cases. So there's another class of microphysical schemes called bin microphysics schemes, and the idea behind the bin microphysics scheme is that you explicitly represent a range of droplet diameters as a single bin, and then you have that bin interact with other bins. Basically, this often is in a kind of a stochastic sense, in that the drops of similar sizes will collide with each other, or drops of very different sizes will collide with each other with some probability, and in doing so, basically that's how you go from small cloud droplets to large raindrops, as the cloud droplets will combine together with each other, and the process called autoconversion. There's also a second process called accretion, where you have a raindrop that runs into cloud droplets and collects them. There's a third process called self-collection, where raindrops collide with each other. So these three processes are kind of the key warm rain processes we're interested in modeling here. And so that's kind of the broad summary of what we're trying to do. The challenge with the bin schemes is that while they have a more physically realistic representation of how things interact, they're also a lot more computationally expensive, because you have to basically have information about each bin instead of like 2 or 3 numbers about the whole distribution like you would with a a bulk microphysics scheme. So what we're what we're aiming to do with this particular data set is run our bin microphysics scheme over a short period or long enough to capture a variety of events with the warm rain formation process. We train a neural network on that to emulate the bin microphysics scheme, and then we plug it back into our parameterization and hope that the neural network runs about the same speed, much faster than the bin scheme, but about the same speed as the bulk scheme. And thus we might be able to run a bin-like thing in a climate model. So if you want to run this notebook on your own, the first thing you'll need to do is make sure all these libraries are installed. We have a convenient command here that you can just run using, like if you're running this in Jupyter Lab, you hit the play button. If you're running this in Google Colab, you would you basically click the cell, click run anyway, and then it will run through this and load everything. There's some things that aren't built into Google Colab, so it'll take a few minutes to load on those. In particular, I think ZAR is one of the dependencies, but it's not in this one. So, yep. I'm going to go back to the Jupyter Lab and run here. And then, so we can go in. Next part is about the data. We have our the model we ran for this was the Community Atmosphere Model version 6, CAM 6 for short, and part of SIAM2. It features a 2-moment stratiform cloud microphysics scheme called MG2 after Morris and Gettleman. And it has liquid, ice, rain, snow, and snow hydrometeor classes, so no grapple. And then it has some other information about microphysics that you can read more details there. And then the key part for what we're trying to model in the MG2 scheme, the two processes we care about, autoconversion and accretion, are represented by these two equations, which the key terms here are QC, which is the cloud-water mixing ratio. So it's kind of a relative mass of cloud water, like a kind of ratio of water, like the total amount of cloud water mass to total, I think, dry air mass. I forget if it's dry air plus cloud. Anyway, the mixing ratio, and then we have the number concentration, which is another term that sort of describes with these two terms you can parameterize your distribution of cloud water. We also have a rainwater mixing ratio and a rainwater number concentration that go along with this. And then the scheme we're emulating is the Tel Aviv University, or TAU model. I described bin schemes earlier, and there's some more information here if you're more interested. There's a bunch of papers and with references at the bottom. We use 32 size bins for our particular implementation of the TAU code, and there's a various little details about how it runs in here. We ran CAM with the TAU scheme embedded in it for 2 years. So we generated a large data set. Basically what we save are the inputs to the microphysics scheme and the outputs of it at a given time step, so that you can basically reconstruct what the microphysics is doing. So we treat the microphysics as a black box in this case, and try to have all the inputs and outputs to that black box. So our inputs, we have our main 4 variables, QC, NC, QR, and NR. We have the row club level is the air density at the center of the grid. So this is kind of to give you rough information about height. We also have cloud fraction and precipitation fraction. So some of these values can be affected by how large of what proportion of the grid cell is is taken up by cloud and precipitation. Since we're running a very coarse grid, this can have an impact on the calculation. We have some other terms in the data set that we're not going to use today, but are here. Lambda and lambda are the slope of the exponential cloud droplet size distribution. So these are other ways of representing our parametric distribution. And then we have the intercept parameter for the raindrop size distribution. And then we have another parameter called the spectral width parameter. This seems to be either 0 or 1, so we're not as useful, but it's in there. We have 4 output variables. For this tutorial, we're only going to focus on QR, which is the rainwater mixing ratio tendency. So how much it will increase or decrease based off of the initial tendency. So this is kilograms per second. And then we have all of our various meta variables. So the meta variables we're not actually going to use for machine learning, but they're helpful if you want to do other kinds of analysis, reconstruct grids, things like that. We also have the tendencies from the MG2 scheme, which we ran in kind of piggyback mode. So it wasn't actually forcing the atmosphere. It was just running alongside to see, given the same inputs, what the output would be as a point of comparison. So now we actually are getting to the main bulk of the code. So first thing we did is we're going to import a bunch of libraries. We also have some different transforms we're going to use for this. You'll notice all these log transforms that are mentioned, and this is important because our microphysics data is kind of exponentially distributed and ranges across multiple orders of magnitude. And so it's a lot easier to work with if you take the log of it. And also things tend to look a lot more linear when you take the log of it for a lot of these microphysical properties. So we're going to take advantage of that. We also are going to have different scalars. So a scalar in this case is just something that will basically normalize your data or rescale the values from, say, 0 to 1 or -1 to 1, or make them have mean 0, standard deviation 1. And these are important for especially for neural network-based machine learning, because our scalars or the neural network weights are initialized close to 0. And so if you give it a bunch of inputs that have really large values, the neural network will sometimes, like the updates of it won't be large enough to get the weights near those values. So bringing the values close to 0 can help with the convergence process. It also, if you have variables that have very different scales associated with them, the network might weigh one variable more than another just because it has a larger range of values. So this helps put everything on a relatively even footing. So it's an important first step, at least for regression or neural network type models. For if you're using a decision tree or random forest, this is a less important thing. So we'll go ahead and run this cell. It should run pretty fast, ish. We also have a lot of other helper functions in here that we'll get into a little bit later. So the first thing we're going to do is we're going to load our data. Currently, our data is sitting in a bucket on Amazon AWS S3. So this is publicly available. It's in what's called Parquet format, which is a binary format that's good for tabular data. It stores it in columnar format. So this is useful if you only want to load certain variables and not the entire data set. It can be a lot faster to load in columnar format. If you're using a CSV file, that will be in kind of more row-oriented format. So it'll load like row by row, which, oh dear. Hold on a second. So so if you're wondering what's going on right now, the authentication timeline just reset for me. So now I have to remember my password. Okay, okay, that was easy. So now we're reloading again. Oh, this is stop. Continues where we left off. So anyway, our data is in AWS S3. We're going to use a program called S3FS. So what S3FS does is it kind of allows you to mount a S3 file system to your notebook or computer, wherever you're at, and then download data directly from S3 into memory. The big advantage of this is you don't have to like download each file to disk first. So it's kind of handy for like temporary stuff, like kind of like you're running on a Google Colab notebook or running here. And we have a lot of basically helper functions that will go through and load the data for us. And what's kind of cool with this is you can actually, like say, use the pandas read parquet function. You just open the file with this S3FS, and then open read parquet operates on this fob. So even though it's not sitting on your computer, you can actually you can read the file, and which I think is kind of cool. We have so next we're going to load our data, which is a kind of involved process, and we're going to speed this up. Right, we have this parallel loading process here, so this will help things go a bit faster. In terms of in jobs, this is one of the key parts of the code. If you only have one processor available, then use one in jobs equal 1. If you have, say, 4 or 8 or however many, I think on Colab, I forget how many you get, but you might be able to get like 2 or 3. So you can try with more than 2 and see what happens. So we're gonna run that cell to activate all the code. Some of the key things that we can do, we load our data in parallel. We then concatenate it together into one big data frame. If we want to subset the data, we can do that with a subsampling. Our next step is we want to transform our output and then scale it. So the transform, basically, we have some code where we specify what transforms we want to do, and this is basically taking the log of the data as our transform, and then our scaling is doing a normalization. So rescaling it for mean 0 and standard deviation 1, and you want to do the log transform first, because if you do it after you make things mean 0 standard deviation 1, then you will have you'll have negative values, and logs and negative values don't mix very well. So we do the log first, and then that also makes the data more Gaussian looking, which will help with this process. So, and there's other fancier transforms you can use to do, besides just doing a logarithmic transform. There's like box Cox, and I think there's some other ones out there. And here we kind of our configuration information for the file. So we specify what inputs we want to load in, the outputs, the metadata, our training and testing start and end periods. This is in hours since the start of the run. So we're loading a subset of the data. And we're also we're using separate training and testing parts of the run for this. And we're also subsampling the data, so we're keeping every 8th file. This is just to keep the memory down on this. Otherwise, the data set's quite large. So if you have a larger computer resources than what you can get in Google Colab, then you could load the full data set. But we want, for what we're doing, this should be sufficient. So we also have we transform our inputs. We also want to transform our output. And what we do here is basically anything less than 1 times 10 to the negative 18, we set to 0, and everything larger, we do a logarithmic transform on it. and this kind of filters out really small mixing ratios that still happen to be in the model because it just allows them to be there, but physically they're meaningless. So now we'll run our data loading, and this should take a couple minutes. We can do the same thing in our over here. So if you're doing this at home, you want to click the, you'll have to go through this little mounting thing, get an authorization code. Then you just put that in there, and then then you can like save stuff to your Google Drive, which is handy. And we'll go ahead and run these cells. So we'll let that run. We'll see if the other one is finished. Oh, it looks like it finished. So it looks like that loaded fine. So cool. So we're also, this kind of saves some of the other information, and we have our mean standard deviation for output here. First thing we do after we load in our data is we want to do a little bit of exploratory data analysis. So in this case, we're going to first run, just make a histogram of our different fields. And this is already on kind of log distributed. So what we see is that our cloud water mixing ratio, we have a bunch of zeros. This is where we don't have any clouds. And then it kind of extends up to about 10 to the negative 4 or so. I think is about the maximum we get here. Then we have NC, QR. QR has a lot more small values in it, and then NR has they all have kind of similar exponential-ish distributions. We have our, we do not do log transforms on the density, the cloud water, the cloud fraction, and the precipitation fraction. In most cases, they are by far either 1 or 0, and with a smaller number somewhere in between. So what does this look like spatially? We can reconstruct our grid from our data files, and you can kind of get a sense of where in the world we are by looking at the row club lev field, because since we're on a model surface, is basically kind of terrain following. So you can see like the Andes Mountains over here and the Himalayas, and then kind of the ocean and land, and although along with some weather patterns. So it kind of mixes everything in together. So we have our basically all of our different variable fields to look at here. So let's see. And basically just a lot of sort of cloud patterns going around the world. You'll notice the precip fraction and cloud fraction are much smaller. So in some cases, even though there are non-zero values in some of these locations, the cloud fraction is really, really tiny. So there's not really clouds here to speak of, or don't have as much of an influence. To get a better sense, we can combine the cloud fraction. We can apply the cloud fraction field as a mask, and then that kind of helps filter out the data to basically where there are primarily clouds. And to get a sense of what the data set looks like, we can also open one of the files, and you can kind of get a sense here of what an example data set looks like. So we'll run that again. And then, so that's kind of a basic overview of our so the kind of data we're working with, kind of problem. Now I want to get to the machine learning. So we've like you also may be wondering at this point, like how do we get to like make all these choices? I mean, there's a lot of experimentation over time, a lot of exploratory data analysis, and looking at the distributions of the variables and kind of the size of the data set. And so there's a lot of choices made along the way just to get through this point that we're kind of glossing over a bit. But I wanted to show some, like, kind of give you a feel for what the data kind of looks like, and some of the inherent complexity in it. So our next step, we're actually going to get to some of the machine learning. For the full system for this project, we have a multi-step process. So you'll notice in a lot of places that there aren't clouds, or there's not going to be any significant change in the cloud, like cloud water, rainwater mixing ratio being added or lost. So to account for this, we have first a classifier neural network model that will try to predict if the tendency is 0 or non-zero. And then if it's non-zero, we will then have a separate regression neural network that will predict the magnitude of the tendency. We have this for each term, so they're all being treated independently, even though they're not completely independent, but we're going to make this assumption for now and hope it works pretty well. For the purpose of this tutorial, we're only going to focus on dqrdt. One thing with dqrdt is that for this process, dqrdt is equal to minus dqcdt. So we actually get to, we have 4 terms we're predicting. That's effectively have only 3 terms because that 4th term is redundant. And so we automatically conserve mass, which is also kind of a nice feature of the problem. So if you can use physics to simplify things a little bit, it helps. Our workhorse for this is going to be this dense neural network class. So this is set up kind of in scikit-learn style using TensorFlow and Keras under the hood. But we've kind of abstracted away a lot of the hard parts. With this, we're just using a fully connected neural network, which means that just densely connected layers. So no convolutions, no recurrent, just a standard neural network. With our framework here, we can specify the number of hidden layers and the number of hidden neurons per hidden layer. So we just assume the same number of hidden neurons per hidden layer. You could do fancier things and increase and decrease if you really wanted to, but we're just going to keep it constant throughout. We can specify the activation function, the output activation, which will be either linear if it's a regression model, or sigmoid if it's a probability, or softmax if it's a multi-class kind of thing. We can add in some other regularizers like Gaussian noise or dropout if we wanted to. We can mess with the batch size. We can change the number of epochs. So epochs is how many iterations through the training data you do. The batch size is to update the weights in our model, we separate our full training set into mini batches that are randomly drawn without replacement from the full training set, and we feed those through the model. Then we have some other things that control the optimizer. Some of the key ones here are so we have a regularizer, L2 or ridge regularization, which we apply to the neurons to help make them more robust to noise and things like that. We also have a learning rate that's an important thing to vary. It's a multiplier to your the expected change in the weights of change in your predicted value, so to how big of a step you make with each weight update. We have separate code that actually builds the neural network. So we have a simple loop that uses Keras TensorFlow, where we have an input layer, we loop through dense layers, and conditionally can add dropout or Gaussian noise. Gaussian noise in this case is additive. You like add like a random value to your data. It can it can help with preventing overfitting to some extent. And then we have a final output layer, and we put that into our model, and we optimize it. Then we have a fit function, which then calls the Keras model fit function, and has some other helper stuff it does beforehand. We have a predict function that's down here that we run the model through and have do predictions. We also have a save Fortran model function that allows us to save it into a netcdf format that we can read with other code and actually run it within the model. So it ends up looking it's like a stripped down version of the Keras HDF5 save model. Also, for those who are participating, if you have questions along the way, please feel free to put them in the chat or into the Q&A. So I haven't seen any, but if anything comes up, please feel free to put your questions in. So we'll go ahead and run this part of the code. We're going to do we defined our hyperparameters, so we can set our number of hidden layers and neurons. We basically just have a big dictionary that allows us to do this. You can try different activation functions, whatever is supported in Keras, different epochs. We're going to stick with these settings because they work pretty well, but I can come back and change them. We also have some other evaluation metrics we're going to look at. So we have a few classification metrics and then some basic regression metrics. We'll talk about these once we train the model. So now we're actually going to train the model. We have some somewhat complicated code to do this. This is designed to do like all of the different processes, but we're just doing QR. So we first train our classifier, and then for the non-zero tendencies, we train the regression only on those. So we'll go ahead and start this so we need to, and yeah, this is what happens when you do last minute changes to your code and don't fully test it out. Luckily, this is an easy fix. So if you're following along at home, that part of the code, you'll need to add a few imports. You can copy them from let's see. Go to ML Microphysics, which is the repository where the code is from. Then you do models, and it would be kind of the first, if you copy the first 5 lines into the code above dense neural network, it will work, or should work. Okay, here we go. And then the training will run through. And this will take a little bit of time to iterate. You should see this loss steadily decreasing if things are working properly. We also have a validation loss, and you'll also see that decreasing. While we're going through that, while we're waiting for it to train, are there any? Does anyone have any questions they want to post to the Q&A or or the chat. So we have one question. Can you repeat why you're dividing into the three ANN classifiers, please? Yes. So in the full version of this problem, there are three different so there's three different tendencies or change in like model state variable quantities that we're trying to predict. So we have the rainwater mixing ratio, the cloud water number concentration, and the rainwater number concentration. And they're all affected by this. They all describe the distributions of our microphysical parameters. And they're all kind of conditional. They don't, like, sometime, depending on the process, they don't all, sometimes they're all zero, but sometimes one or more of them is non-zero and the other ones are zero. There's kind of three microphysical processes we have to worry about. So autoconversion, we have cloud droplets combining together to form raindrops. So in that case, basically you have the cloud droplets, so your cloud water mixing ratio will decrease, your rainwater mixing ratio will increase, and your number concentration will also change in some way. Basically, you'll have fewer cloud droplets, and the small ones will go away. So that affects the kind of the shape of the distribution a little bit. You also, with accretion, you also will lose cloud droplet mass and increase rainwater mass. And there's a third tendency called self-collection, where raindrops collide with raindrops. In that case, the cloud water doesn't change at all, but the rainwater mass doesn't change, but the rainwater number concentration will change because you'll have fewer raindrops because some of the raindrops have collided with each other. So because of this. Of these different effects, there are multiple processes being acted on by the neural network has to learn about. We decided that the best approach for this is to separate the terms into this classifier step and the regression step. Will the recording of the seminar be available? Yeah, so the notebook files are in this AI for ESS hackathon. If you logged in late, I don't know if the earlier part of the chat got through, so I'll go ahead and reshare the link. So if you go here, the challenge notebooks are there. There's also links to Google Colab, so you can update it. The full microphysics code, if you want to like kind of experiment and see some of the more gory details of it, is located here. And then we had a paper come out on or just appear in the Earth Archive, and I'm going to my Twitter because the link is on my Twitter and it's easier to find it here. So we have a paper on this that is, I'll post that in the chat. So if you want to read more about all the details and kind of some of our climate model results, you can go there. And so now we should have finished training the model. Try again. The joys of live demos. So we got almost to the end, but then it failed right there. But luckily this one trains pretty fast. In the meantime, we can look at some of this other code that already has visualizations put into it. So what we should expect to see with our classifier model loss, kind of the trajectory over time, is that we should see it steadily decreasing. And this is the loss we're using for the classifier is binary cross entropy, which is a pretty standard classification loss that looks at like kind of the log of the probability distribution, discrete probability distribution, and kind of you wanted to separate your classes nicely. And so we see it steadily decreasing, which is what you hope to see. We have both training and validation sets. So the idea behind this is that it's easy for a machine learning model to overfit. And overfitting usually means that your model is fitting to noise in the data, so it's coming up with an overly complex kind of curve that it's fitting to the data. And that curve will not it'll fit well to the data you've trained the optimized the model on, but when you give a new data it hasn't seen before in kind of that same space, it will do poorly. It'll have high errors. It'll make large changes in the prediction with small changes in the input, which is usually not desirable. So one way to make sure that it's not doing that is to have a validation set, and we compare the validation and training errors to make sure they're both decreasing. Sometimes you'll see the training error continue to decrease while the validation error stays flat or goes up, and that's usually a sign that you're starting to overfit. So now it should still be running. So it's going to, now it's going to start on the regression model. This one will go faster because it has less data that has to work on. So notice this took 10 seconds per epoch, and now this is taking 4. I don't know if you can hear it in the on the audio, but we're actually having a little bit of a thunderstorm coming through here. So it's appropriate that we're having a discussion on rain and clouds while we have rain and clouds outside. So I'm glad the weather is cooperating, and also that it's a decent little storm that's coming over us. Nothing that's concerning me too much though. If it gets particularly exciting outside, I'll share the view. But so our curve looks pretty similar to before. It's going to be a little different every time, and if you run it yourself, it'll also be a little bit different for you. I think it should be mostly the same because we have a random seed fixed in here, but it might end up being a little different for you. Or if you rerun it multiple times, it'll definitely be different. So the first way we're going to evaluate this is we're going to look at our classification performance. We're going to use what's called this, start with our contingency table or confusion matrix. In this case, we're using the one from scikit-learn. So it's a little bit different from, say, the meteorology one. The way you can read this is this box, the upper left, or row 0, 0 in your array are true negatives. So this is where there are no cloud, no change is predicted, and no change occurred. This box is the true positive, so this is where there were non-zero tendencies. And then, so this is where we have, trying to remember the ordering here. So this is the rows are observed and the columns are predicted. So this is predicted true tendency, but this is false alarms basically, and then this is our false negatives. So these are non-zero tendencies that our model missed. In terms of our statistics, we seem to be really good. I mean, we have our probability of detection, which is the the ratio of true positives to all observed positive tendencies was 97%. Our success ratio, which is the ratio of true positives to all the predicted, so basically this number divided by the sum of this column. This is really high. Our model is fairly unbiased. It has a frequency bias, which is the sum of the true positives and false alarms divided by true positives and false negatives of 99%, or 0.99. So it seems to be really good. We could probably make it a little bit better with further training and refinement. Next thing we want to look at is how will we capture the distribution of predicted versus observed or simulated tendencies, and we seem to do a pretty good job with that. This is in log space, and then we can also look at it in linear space. This kind of emphasizes the peaks better. The other version emphasizes the tails a little better. But we're generally capturing the distribution well. We can also look at our relative errors in terms of 2D histogram. So this is on a log scale, but basically our emulated tendencies versus our actual tendencies. And by far, most of the examples are on our one-to-one line, but we do have a number of cases where we have some pretty large deviations. So our model isn't perfectly capturing the system, but for the most of the time it is. And we hope that some of these cases where it's further off, that there might be some instances where it could be a problem in our emulation, where if there's enough of those that occur at the same time, we can make the model unstable potentially. But most of the time we're doing really well. We can also look at kind of a distribution of the residuals and see some of the, basically you see that, I should mention also for all these that these are on a log scale. So this is like actually, in the model, this would be like 10 to the negative 8, 10 to the negative 6 kilogram per kilogram. So all these are actually really small values, and most of the time the tendencies are all really small, but you add up enough of these tendencies and that can make a difference over time. In some cases we can be off by like 5 orders of magnitude, which also sounds kind of bad, but some of those I think are coming from some of these larger errors over here. So good, but I think room for improvement, especially on the far end of the scale. If you look at this on like kind of a non-log scale, by far most of the time we're right on. So which one matters to you is, it kind of depends on what you care about with this problem. We can do some further analysis in addition to our evaluation by looking at machine learning interpretation methods. So the motivation behind interpretation is that we want to look at properties, basically, whether it be what the model has learned, so in the sense of what variables it thinks are important, where are the sensitivities of the model in kind of a lower dimensional space. There's a number of different ways we can kind of investigate this. So the first is permutation variable importance. I have a nice little animated GIF that explains how this works. The basic idea is that first you pass through your say your training or testing data through your trained model, and it makes a set of predictions, and you calculate some kind of error on it. Then you want to see your in this case, our measure of importance is how, if you basically randomize one of the fields by shuffling it, what this does is it keeps some same distribution over the data set, but removes the information content of that variable because we've now like displaced the value to a different example that has no connection to. So when you do this, like if the variable is important, you would expect a large decrease in accuracy or a large like increase in your root mean squared error or whatever. And so we can do this for every variable in sequence and get an estimate of how much each one decreases, and that gives us a rough estimate of the importance of that variable. Why would you want to do this? The benefits of this method are that it's model agnostic, so that you can apply this to any machine learning model or any function really. You perturb basically you treat the model as a black box, you perturb the input and see what happens on the output end, and that gives you some information about the model itself. And it doesn't depend on the model structure, so you don't have to look at weights or try to interpret weights or anything like that. It's all kind of every model will be on the same playing field that you apply it to. You can also use different subsets of your data set and see how the importance of the variables varies depending on different, say, regimes. If your data set has particular regimes in it. So we can run this in our code. If you use scikit-learn in their inspection module, they have built-in permutation importance as a function in the newer versions of scikit-learn. So you can write your own machine learning model and feed it in there, and then you just pass your training and labels and a scoring function, and then we can run it. And it'll take a little bit of time, but you'll get you can also run it multiple times. For this, we're just running it once. Ideally, you run the process multiple times, since the random shuffle you'll get a different importance score depending on the shuffle, because it is stochastic. So it's good to run it multiple times and get a distribution. That can also give you some uncertainty bounds on your importance, which can be helpful. What we can see with this, that our cloud water mixing ratio is deemed the most important variable, followed by the rainwater mixing number concentration, and then the cloud water mixing ratio. They all had non-zero importance, so that's good to see. Sometimes as a test, you may want to throw in like a completely random variable, just to, because sometimes you'll get non-zero importance variables that actually aren't important at all, and so it can be helpful to sometimes throw a junk variable in as kind of a way to verify that. We can do the same calculation on our regression model, and we'll see, you can see how the importance varies depending on the choice of model. The precipitation fraction is less important, but still not insignificant. And we see this actually appears to be the most important variable for doing the regression. And this one has actually had a fair bit of variation depending on doing the training, so that's also kind of interesting. The downside, one of the downsides of variable importance, though, is that it doesn't really tell you much about why the variable is important. To assess that, we can use a different method called a partial dependence plot. With the partial dependence plot, the code for it is actually very straightforward. This is the entire function right here. It's 6 lines, but what it does is kind of intense. So first we make a copy of our data set. So we have a mp.copy here. We then loop through, we pick a set of values. So this can be like just points along the line. So usually ranging from like your minimum training data value to your maximum, but it could be, you can stretch it out beyond that and see how your model extrapolates even. But for each of those values, you take your copy of your data set, you pick the variable you're interested in seeing the dependence on, and you set every single value for all examples to the same fixed value. And then this is basically our perturbation to the data set. Then we feed the data through our model, we make a prediction, and we collect the predictions for all of our examples, and then we try a different value, we loop through, and we repeat this process over and over again, and we do this for every variable. So we'll go ahead and run this. So we'll go ahead and run this. This will take a little bit of time to iterate. But as it's iterating, what we should see is something that looks like this. If you take the mean across all your predictions, you'll get the main, called the partial dependence curve. Where the curve is relatively flat, this means that if you change your input value, the change in the average predicted value from the data set should be very small. Basically, like this part of the input space on average is not very important. But when you get to a larger values, you'll see that the basically we start having a stronger dependence. And so in this case, like around 10 to the -9, we see our curve start going up. For the benefit of some other information, we also have our probably the 90th percentile kind of prediction sort of output interval from our curve. So we have a separate curve for every single data point, so we can aggregate them together and see what the range is. When you have a smaller range, that means basically everything is behaving more similarly and having a stronger impact. Where you have a large range, that's where there's less sensitivity to that variable, because it's basically every variable is just like whatever the predicted value was, it's still that same value. So it can kind of give us a sense of the also the importance of that of the variable at the same time. And we can see that some of the variables that have higher permutation importance usually tend to have more interesting partial dependence curves. So like our row club, lev, which had a very low importance, also, yeah, it doesn't vary very much at all in terms of the partial dependence. In this one, the precipitation fraction doesn't vary much, but it may be different in our with this newer model. So we'll have to run and see, but we'll come back to it. One of the cool things you can do with partial dependence, because it is model agnostic, we could also apply it to, say, the MG2, our coded version up of the MG2 auto conversion and accretion. So wrote up a little function that does this. Also did partial dependence on it, and now the red curve is the partial dependence curves from up here, and the blue curve is now MG2. So we can see where the curve, since we apply the same data to it, we can see where the curves overlap with each other and where they're very different. So for large values of QC, we see that there's actually a fair bit of overlap in our in the average predictions. And then for QR, also at larger values, we see an overlap, but we also see some significant differences, especially at the smaller values, which is good to know. And so we could use this to compare, like, say, different machine learning models. We can compare the actual, like, the true bin microphysics with the emulator. There's a lot of different ways you could do statistical comparisons and go nuts with different permutation tests and all kinds of other stuff to quantify exactly how similar or different they are. So I think this is a pretty powerful method that there's still a lot that can be done with it, and people are kind of exploring it more. There's also a bunch of variations on partial dependence plots that have other advantages and disadvantages associated with them. If you're interested, if you want to read up more on this, there's a book called Interpretable Machine Learning by Christoph Molnar, freely available online. There's a whole section on model agnostic methods, and that goes into more detail about all the nitty-gritty of all these, of how all these different things work, including partial dependence plots, and it talks about advantages and disadvantages. There's the other popular version of this is something called accumulated local effects, or ALE plots, which look at kind of the derivative instead of the exact predicted value. So it's a little bit more robust, but a little bit harder to implement. So those are the things available. This is kind of the end of this notebook. I encourage you, if you want to kind of play around more with it, with the data set. Oh, good. Let's see if it finished running yet. Nope, almost there. Feel free to run this in Google Colab on your own. I'll push the couple of changes I had to make after the tutorial, so that it does in fact run for everyone. Now we can see what the curves look like. Drum roll. Okay, now we see. Actually have an interesting like kind of inverse curve between precip fraction and the cloud fraction, which is good to see. but yeah, our QC talon curve looks pretty similar, as well as QR talon. So there you have it. This is the kind of microphysics portion. I'm happy to take more questions in the chat if you about microphysics or anything I kind of skimmed over. Feel free to put in questions. And yeah, if it takes you, I know it can take a second to type things in, but while if you are typing in questions, we're going to go ahead and move to the next notebook, which is the HOLODEC notebook. If you're to access it, oh, here we go. Regarding permutation and feature importance, is this different ranking of precipitation and feature importance dependent on properties of distributions like mean squared error penalizing outliers more heavily? So you got a less Gaussian variable and might assume an outsized apparent importance, or has you transforming addressed that? For permutation importance, the distribution of the variable is less important. I think the choice of loss function can be important. You will get a different ranking based if you use a different loss function, because they like, so if you use mean squared error versus mean absolute error, you may get a different ranking. So it's important. It's good to do it like multiple times and potentially even like resample your data set and redo it, or kind of, if you want to be more robust about it, maybe retrain your model multiple times and try it. It is computationally intensive because you have to do all this shuffling and passing all your data through. So that's something to take into account with it. And it's also meant to be a kind of a global measure of importance. So with global measures of importance, that like they'll be kind of biased toward the majority class of how it behaves. So if you have important other sub regimes that where the mix of variables may be very different. If you eliminate variables that have relatively low importance but happen to be important in those subregimes, then you could make your model worse, even though you're supposedly eliminating unimportant variables. So that's something to watch out for when, say, using feature importance as a method of variable selection. But that's also true for any other variable selection method. So something to be aware of. So with we're going to next go to the holodeck. If you go back to if we go to the links, there's also a holodeck link. You can open it in Colab, and it will, you should get this kind of thing to spin up. I'm going to run the Jupyter lab, but it looks pretty similar. Mostly runs the same. The neural network in it trains a bit slower on Colab we haven't entirely figured out the reason why. But if you do have access to a GPU on another system, then it might be useful there. We are using a CNN for this, so we get to go into some deep learning. So first we get some pretty pictures, and we get to find out what we've gone from. This is going from model world to observations, but we're still in the clouds. The Holodeck Probe is this instrument that flies on things like the NCAR Gulfstream or the C-130. In principle, the instrument is somewhat straightforward. You have on one end you have a laser, and on the other end you have a camera. You shoot the laser. Basically, the laser shoots through kind of this path, like kind of small volume between kind of in front of this probe. And so as the plane is flying through a cloud, the laser hits cloud droplets, raindrops, ice crystals that are in the path, and then you get the laser diffracts off of the crystal, and so the diffraction pattern. So basically, you get these kind of waves that emanate like ripples on a pond, and then the ripples reach the camera, which is just kind of like your standard camera, but it's a holographic camera, so it captures the ripples. And what we can do with these ripples is we can there's an analytical process to basically refocus the crystal at different distances from the camera, so that we can actually reconstruct from these ripples the actual shape and size of the particles. You analytically do this like 1,000 times at different points, and you go from something that looks blurry like this to a picture that looks more like this. And so, like the big benefit of this instrument is that we can get like basically pictures of ice crystals and stuff and get really fine structure much better than more traditional probes where they basically put the camera on like facing forward, and then your cloud particles and raindrops collide with the lens. The problem is when your plane's flying hundreds of miles an hour through your cloud, and basically you blow up the particles when you do this. Whereas with this, the particles we capture them as they fly by. The downside of this approach is that it generates a ton of data. Like it's taking a multi-megapixel image every second, I think, or sub-second. I forget the exact frequency. It's probably in here somewhere. But it's a lot of data. It takes like a week for one flight. It takes like a week on Cheyenne to process all of the images. So the motivation behind this is that we want to speed up this process so we can, because what we want to get out are the locations, depth, and in particular the sizes of the diameters of these particles, so that we can get observations of particle size distributions in situ in clouds that we can use to calibrate our microphysics schemes and our weather and climate models. And so we have an example of some particles here. So we can we have an original image, and then we can reconstruct it by refocusing on each particle. And then as you do that, the particle kind of comes into focus. And then we saw these other ripples from around it otherwise. And we have some other fun visuals of this. To get some intuition about like what the ripples mean for particle sizes and stuff. Obviously, if you have a bigger particle, the size of the ripples is a function of both the particle size and the distance from the camera. So the further away the particle is, the bigger the ripples will be, because basically they've traveled more. But if you have multiple particles, one of the challenges is that the ripples kind of interact with each other. So you get these complex interference patterns that can make it harder to tease out exactly the size and locations of the particles. So it's an interesting inversion problem to get back the things we care about. So first, we make sure we load in all of our data sets. And then the data we're using is not actual holodeck data. We're using synthetic data, so we don't have to worry about noise and speckles and dust on the lens and things like that. But it's still hard enough. We have multiple versions of the data set. One is a single particle data set, which is pretty easy. The ripples are emanating from the single particle. But we also have we're going to focus on a multi-particle data set where there are between, I think, 1 and 3 or 1 and 5 particles in the image. And so there's some information about the data set, how many holograms we have and how many particles. These are all now online on the cloud as well. So we'll go ahead and import everything. We're going to use our GPU. So one thing that if you're sharing GPUs with people, a nice thing to do is to, if you're using TensorFlow, to get your list of GPUs and then change the set memory growth attribute to true. What this is good for is doing things like, say, if you don't want to, by default, TensorFlow will grab all the memory on the GPU. If you don't want it to do that, it's good to set this up, especially if you're running, say, multiple notebooks in parallel or things like that. So the next part, we're going to load in our data. We have basically just some helper code that loads in the data for us. It'll automatically also scale the data. So we're just going to scale it by the minimum and maximum values just to make things easier. You could try other ways to do this if you wanted. And we're also going to rescale our outputs. The output, so the output we're going to focus on, while we have data for the X, Y, Z positions of the particles, we also have the diameters recorded. Since this is synthetic data, we put the particles, we generate random locations for the particles, and then we run our pseudo holodeck or synthetic holodeck and generate the synthetic imagery from with this information. So we have perfect knowledge of where all the particles are, which is also a nice benefit. But what we're going to focus on is predicting Z, and we're going to do this in a discrete sense. So we're going to try to say we predict that there's a particle in this range of Z values. And this is useful because then instead of having to do, like, say, 1,000 reconstructions of the hologram, we can use the neural network to say, only look in these areas. And then, so you only have to maybe run like 100 or 10 or some smaller subset of reconstructions to get where the particles are. And that would speed up your process by a few orders of magnitude, potentially. Unless there's a whole bunch of particles, and then but a lot of times, especially with ice particles, there's only a few particles, and so being able to reduce that computation would help speed up the process quite a bit. So we're going to load in our data. We're going to make a plot of a hologram just to give you a sense of how everything looks. So this will take a second to load, but we're just calling our load raw datasets function. We have training and validation data. Our plotting function, we're going to plot the hologram itself as well as kind of particles overlaid on it. So we have the ripples from the particles. Then we have 3 particles in this one. Although it looks like there's another ripple here. So I'm not sure if that's if there's actually a particle there, if that's like just a weird interaction with everything else. We can change the number, and you can see like hologram 204. And maybe it's just something weird in the code where it's not plotting all of the let's see something. No, yeah. Now we're going to load in our normalized data, so this will take a second. While this is loading, we can talk about our machine learning model for this project. So we're going to use a convolutional neural network. So before we used a fully connected neural network, and the advantage of the fully connected neural network is that it's relatively simple and straightforward. But if you want to apply it to an image, if you're trying to connect like a neural network weight to every single pixel, the dimensionality is going to grow quite large, and you're going to have a lot of redundant weights, and it's going to be slow to learn. I mean, you can still do it; it'll still work, sort of, but if you can make certain assumptions about the properties of your data, like say with particles, they could be anywhere in the image. They're kind of localized. They have certain patterns that are associated with them. We can then reconfigure our neural network to focus on looking for localized spatial patterns, and it does too with what are called convolutions. I can. So it's a pretty straightforward kind of thing. Let's see. Okay, our data is loaded. So our convolutional neural network function, we have a set of, we specify the number of filters in each convolutional layer. We also specify kernel sizes. So our kernel is basically like a 3x3 pixel or 5x5 pixel box that we move over our image. So it goes like, then if you can see my hand kind of going over the screen, sort of goes back and forth. And what it's essentially doing is just multiplying the filter weight by the image values and then summing them up together in that local area, and then that outputs a single value. And when the value when the filter lines up well with some feature in the image, you should get large values, and when it doesn't line up, you'll get small or negative values. And you can use this to selectively basically light up different parts of the image that match up with this pattern. Because there are a lot of patterns one might be looking for, you often have different multiple convolutional filters that you learn about your data. You can also then stack a series of convolutional filters, and then they can learn higher level representations of the data by combining the outputs of other convolutions. The other thing we also do is it's called a pooling layer. So pooling is just taking a spatial like average. So like take the average of like a 2x2 box, or you can take the max in a 2x2 box, and that compresses the information about the model into a smaller space. And then if you run a convolutional filter over that pooled image, the same size convolutional filter from before will cover double or more, a larger portion of the image. And so this is useful for basically keeping your model size relatively small, but still capturing information across multiple scales. And then otherwise, a lot of the parameters are pretty similar to what we used before in our densely connected neural network. With this, we also follow the scikit-learn style function or a machine learning model declaration, where we specify all of our model parameters up front. And then we have code that will build the neural network by combining convolution and pooling layers, and then we flatten them out, and we have a series of dense fully connected layers after that. And then our final output model, we optimize, fit it, and then we'll talk about some of the other interpretation stuff in a second. So we'll define this. We'll also have some custom metrics. So we'll actually keep track of contingency table metrics, but in a different context. So we're kind of making a prediction of where particles are and where they aren't. And so if we pick a threshold that's like 1 divided by the number of bins, essentially, if our model has any skill at localizing where these particles are, it should predict the higher probability certain bins over other bins. And so we can actually keep track of how well the model is capturing all the different bins. And so we're going to kind of use a contingency table approach for that, because then we can calculate lots of fun skill scores and other metrics from that. So now we'll train our model. And we specify the settings here. So we use 4, then 8, then 16 convolutional filters. We use a 5x5 convolutional kernel, a rectified linear unit activation function, pooling sizes of 4, 4, and 4, and then dense layers of 64 and 32 hidden neurons. These are settings that seem to work pretty well before. You can, if you want to run this at home, you can mess with them and try something different. We have a specify our learning rate. We also have something called learning rate decay, which we like after each epoch, we reduce the learning rate by like 10%. And in doing so, this helps the model, this can sometimes help the model zero in on good performance. And then, yeah, just, let's see. We also specify a batch size. So in this problem, because the data is kind of large, you want to use a small batch size, or else you might run out of memory on your Google Colab notebook. Okay, what do we do? See if this works this time. Hmm. Yeah, this is odd because it was just working before, so I'm not sure what happened here. So we're going to let this run and see, see if this will work. Okay. So I just did run some Chrome. That was training. It should, as it's running, we can keep track of all the different metrics. One thing we'll see is that our, like, initially it stays pretty flat for a little bit. Like, our loss is not really changing much, but then at some point in the training process, it will start learning. So we have an example of the training curve down here from a previous run. And it may be that the learning rate, messing with that, eventually knocks it loose. And hopefully it'll actually do that this time. And as the nature of a lot of live demos, in this case, it doesn't actually seem to be error. It doesn't seem to be dropping. I'm going to try again. We're going to stop and And does anyone have any questions at this point while we're watching training going on? Oh, here we go. So the question is, your loss curve diagnostic, what does learning effectively look like? Is divergence of training and validation lines seen in your example from the previous run good or bad? Usually, so where you start seeing the divergence, that's usually kind of a bad sign. That essentially is telling you when overfitting is starting to occur. So in this case, the training error continues to get lower, but then this is where when the validation error starts departing from the training error, that's a sign of when your performance is like there's like the model is fitting to noise in the training data, and thus you'll need to do like retrain some different model parameters. Some of the things you can change are, I mean, one of them is things like varying the learning rate, but you also may want to decrease the complexity of your model or keep the same complexity but add regularization, whether it be a simple regularization like an L2 norm or L1 norm, or adding things like dropout or other noise. Those are typical ways to deal with overfitting. There's also a whole area called data augmentation, where you take the same images, or you take your data and you like say rotate it around, or shift it around a little bit, or add some random noise to it. And some of those can you basically just make duplicates of your original data set and feed it through with slight differences, and that can help with your deep learning training performance. So we can look at this one, and we see that we get some severe overfitting. Basically, it gets better and then it gets worse again. We can look at our confusion matrix, and in this case, we do see a like so our true positive rate stays pretty flat, but our false positives go down. And I'm not sure if HIST is taking into account the validation or the. It's a good question. Let's see. So if we, so this is the training version of this, why it looks like it's getting better. But then if you do the testing version, basically we see our true negatives go up, false positives still go down, and everything else is still relatively flat. It's a little bit noisier too, I think, because there's also fewer validation examples. So that's also something to take into account. So we can also look at kind of individual predictions, and we can see, so ideally we like to see the red bars line up with the blue bars. We see we're pretty close. It's picking up a third particle in here in the middle, and it has higher values than the bin next to where the actual bin is. So I mean, pretty good, but definitely room for improvement. And we can look at some different examples, and this one, it's a lot more uncertain about where the particle is. So it also has a wide, like it has probabilities across more bins. This is like visualizing individual examples. This is a helpful way to learn more about your data and what's going on in it. We can also look at our predicted versus observed Z distributions. And what we'd ideally like to see is, with this data set, you would assume that since it's a synthetic data set where we sampled uniformly across the Z values, this should be pretty flat. But our predicted distribution has a bit more variation in it. It's under predicting the middle and over predicting at the extremes. So this is also something we can look at and kind of use it sort of like a rank histogram in an ensemble and see subjectively whether we have any biases in terms of where it's focusing its attention on. We can also look at other metrics like the rank probability score, which will give us a sense of if we have skill at identifying particle location, and we do appear to have some skill. It's not great, especially compared with other I've gotten up to like 0.7 or so on, or we've gotten up to 0.7 on this. So this is just not a particularly great run. There's a fair bit of uncertainty with the whole process. So good to run, do more hyperparameter tuning and validation and trying different. There's a lot of different parameters settings you can get on this. But one kind of cool thing you can do on the interpretation side is we can actually look at where in the holodeck image the model is giving its attention. We can use a method called saliency maps to do this. All a saliency map is that we take an image, we send it through our neural network, and we look at the output of a particular neuron. It could be an output neuron, it could be a neuron somewhere in the middle. And in the process, we can then do back propagation, which is the neural network optimization process, and we can calculate the derivative with respect to that particular neuron on the input image. So you can do the change in the loss with respect to the change in the input. We can make a map of that and overlay it on our actual inputs. And so we're going to look for where our Z bin number 8, which is, so we have 10 bins, 0 through 9. So this is like kind of near the far end. We're going to find neurons that activate this. The model predicts high values for high probabilities for bin 8. And then so we'll pick the top 9 of those. We then run our saliency function on it. And then we can actually make a visual of where the model is focusing its attention when it's doing this. And ideally, we should see like hopefully the model is focusing its attention in the vicinity of where the particle is. And in this example, it appears to actually be kind of doing so. We see it. Well, it's not focusing on somewhat focusing on the particle itself, but it's more focusing on these on the rings. It's doing so on the rings that are actually near the particle, so that's kind of good to see. It's sort of a nice sanity check that you would hope it would be doing that. Although it's not perfect for like in the first image, doesn't seem to have any saliency at all. Whereas in the other images, it seems to be doing a little bit better. And it could be because just this particles are at different locations. We can also do we can pick a different neuron. So we can pick one that's like kind of close to the camera. So it'll be like neuron 2 or bin 2, and then we rerun the same thing. And in this case, we don't see nearly as much saliency. We do get some like around this particle here. Other ones don't seem to be showing up as well. And it may not be, or it's only focusing a little bit of attention. But it may be a sign that or also maybe that my threshold is a little high. So let's see what happens if I lower it a little bit. Okay. So some of this is a visualization issue. So now when we lower it a lot more, we can kind of get a sense of where basically it does seem to be surrounding the particles themselves, which is good to see. But it's also picking up on where things like the upper edge of the image. So further optimization, I think, would get better results. And usually, like one thing you sometimes will see with saliency maps is that with a well-optimized model, it will key in on things, and if it's not well optimized, it won't. But there's definitely a lot of room for further interpretation with these. But it's another tool we can use for this. Yeah, feel free to try different model settings. Like we could try. We have a little bit of time to do like one more experiment. So let's play with a couple parameters. See if any of these actually make a difference. And while we're doing this, happy to take more questions on this notebook or any of the previous notebooks or any other general machine learning questions that anyone may have. What do you learn from the confusion matrix history? The example looked like there was a sharp increase in the true negatives at some point, but wasn't the same saturation regarding CF overfitting impression as in the model loss. Yeah, in this case, it didn't seem to make it did track with the model loss pretty well, which you would kind of hope it does. Some of the idea behind the metric was to try to get a sense if it could more finely like measure, say, the uncertainty in the prediction. So like if it has a lot of uncertainty, then it's going to have a lot of false alarm area. But then as it got more certain, the false alarms would decrease. And the hope is that if it's actually learning something, then so in this case, it was pretty flat through the whole training period, and then pretty flat there. Ideally, what you want to see is that your POFD and FAR would decrease at some point, whereas this they're remaining fairly constant throughout, which is less ideal. You do want to see that change, and it looks like that the loss itself captures it well. But with the contingency table, you can break it down more finely into false positives versus false negatives. Because what you wouldn't want to see is say is your false positives decreasing, but then your false negatives increasing because you're starting to miss where the particles are. That's kind of the motivation behind using that. So yeah, we're gonna try to go in a different direction to see if this does anything on the training front. I say this is less efficient than a full a more proper automatic hyperparameter search on this problem. And given that I don't have as good intuition on it, like doing more automatic hyperparameter searching is valuable. There's some different ways you can do it. One is it's called a grid search. The most basic one is you pick some values and you do a brute force search over all the values, and you pick whatever result gets you the best one. But there's also there's smarter approaches. There's also like random search where you randomly sample different values, and then that gives you a sense of the loss surface, and you can try to interpolate within that loss surface to see if you can find any potential local maxima or whatever. And there's approaches that allow you to do more sampling and other stuff to get there. Yeah, for this particular problem, it looks like we're just it's harder to stumble upon the part of the surface where you actually want to optimize. Oh, I found it. Any other questions from anyone else while we're waiting for this last round to train? Oh, I was saying the loss finally started decreasing when I said I found it. If you're looking at the loss size as they track through, it finally started decreasing again. And so when it was pretty flat for a while, and then suddenly at pick 24, it started going down. And so we should see a similar trend in here, and yeah, right around the same time, or the true negatives start going up. Basically, it means the model is like when the true negatives start going up and the false positives start going down, they're kind of proportionally. That means the model is getting more precise and accurate in its predictions. And since it's doing so without the POD going down or staying roughly the same, it's actually learning something. So we have now we can see if these look any different, and they do look a little different. And you can see what our rank probability score looks like. We got a little bit better, 0.65 this time. So then we can also do this saliency calculation. And now we're seeing focusing a lot on kind of the areas around each particle and kind of these concentric rings. I added a Gaussian filter to kind of smooth out some of the activation, which is why you see some of the little boxiness associated with it. The actual, if I turn off the Gaussian filter, it'll look a little better, or it'll look it won't be as smooth, but it will. We'll see what it looks like. Actually, it doesn't look too bad. Is there a class imbalance problem here given low true positive rate? Seems quite common. Theoretically, there shouldn't be because we're uniformly sampled every single bin. So there's the particles are equally distributed, although they're based off of the distribution, there shouldn't be a class imbalance problem. But I mean, there is kind of a rare event problem in that there's only one or two classes at a given time since it's a multi-particle distribution. I think having more data would probably, we're training on a relatively small subset of the data set, and that that's also not helping performance, but the images are quite large. One other thing we could do is reduce the size of the images by subsampling them, downsampling them a bit, and we could see if that helps with performance potentially. Because the things we're looking at are these kind of rings, and there's quite a few of them. We could resolve them with a coarser image, and still I think get the important information out of it. Yeah. So this is all we have here. Again, the data sets are available online. I'm going to check in these changes real fast, so that if you want to go to this later, it'll be they'll be available and everything should work. So let's see. Also, if you have more questions, my email, I'll put in the chat, is dgagne@ucar.edu. I'm on Twitter at djgagnedos. If you want to, if you have more questions or want to follow up with anything, please feel free to reach out to me there. With that, I'll take any final questions, but otherwise I think we can go ahead and wrap up. Thank you very much for joining us today, and I hope you have a great afternoon or evening or morning, wherever you are calling in from.